On July 1st, 2025, under the thin air and bone-dry peaks of Chile's Atacama Desert, a robotic sentinel named Atlas swept its electronic gaze across the heavens. The Asteroid terrestrial impact last alert system built to guard humanity from celestial threats had long been cataloguing wandering stones that might one day set their sights on Earth. But that night, the telescope's sensor caught something stranger, a pinprick of light gliding against the starfields of Sagittarius. It was faint, almost insignificant, yet its motion betrayed a secret. Within a single day, NASA's best analysts had crunched the data. What emerged from their equations was enough to send a jolt through observatories worldwide. This was no ordinary asteroid, no icy remnant bound to our sun's gravity. It was an emissary from the deep beyond. The official designation soon followed. 3I Atlas, formerly catalogued as C2025N1. The prefix 3I marked it as only the third confirmed interstellar visitor in all of recorded history. Reflect on that. Across centuries of skywatching, billions of comets and asteroids have been charted, and yet only 3 times has the cosmos delivered a traveler that does not belong to our solar clan. The evidence lay in the numbers. Interstellar identity is written not in surface features, but in mathematics. When researchers traced the object's orbit backwards through the tapestry of space-time, they found a trajectory so radical it could never have been sculpted by our sun or planets. Its orbital eccentricity was calculated at 6.1, a staggering figure. For comparison, Earth's orbit is a near-perfect circle with an eccentricity of just 0.017, and even the wildest long-period comets seldom exceed 1. Atlas's path was not just unusual, it was hyperbolic, a curve so extreme it could only mean one thing. This visitor was born outside the gravitational walls of our solar system. Its speed confirmed the verdict. Racing inward at nearly 60 kilometers per second, over 200,000 kilometers an hour, Atlas was moving too fast for any planetary slingshot to explain. This was momentum gathered over galactic distances, a plunge that may have begun millions, perhaps billions of years ago. And its entry point only deepened the mystery. By tracing its arc backward, astronomers found it descending from the direction of Sagittarius, a region pointing toward the crowded stellar neighborhoods near the Milky Way's core. Unlike the Sun's quiet suburban orbit, the galactic center is ancient, turbulent, and full of gravitational entanglements. What kind of birthplace had shaped this wanderer before casting it into interstellar exile? As always, the question of danger surfaced quickly. Was this alien stone hurtling toward us? The answer brought relief. Earth was never in the crosshairs. Its closest passage would come in December 2025, at a safe 1.8 astronomical units, about 270 million kilometers away. That is well beyond the distance to Mars, leaving humanity as distant observers. Yet safety for Earth did not mean safety for the object. The true trial awaited it near the Sunday. Atlas was bound for perihelion, the closest point to the star, arriving around October 29th-30th, 2025. At that moment it would skim through the inner solar system, passing just 1.36 to 1.4 astronomical units from the solar surface. For something forged in the frozen interstellar void, untouched by warmth for eons, this close brush with stellar fire would be nothing short of transformative. Here, in the light of our sun, a fragment of the galaxy itself was about to reveal its endurance or its fragility, and the world was watching. Long before it reached the asteroid belt, the first signs of awakening began to ripple across 3I Atlas. Telescopes caught whispers of change, frozen ices, locked away for billions of years, stirring under the heat of our Sunday. At first, it was only a shimmer, a thin veil of gas and dust that clung to the nucleus like breath in winter air. But day by day, the glow expanded, forming a delicate coma. Soon, a faint tail extended outward, not unlike the ghostly outline of a traveler announcing its arrival to the solar stage. On the 27th of August, 2025, the Gemini South Telescope captured color images of this transformation, the subtle hues revealing that these were not ordinary cometary gases. What we saw hinted at chemistry born under alien skies, forged in conditions far from anything familiar within our solar family. Measuring its body proved a puzzle. Estimates placed the nucleus somewhere between a few kilometers and over 10 kilometers across, larger than the enigmatic Oumuamua, yet still small enough to vanish inside a modern city's limits. But scale is deceptive in the cosmos. What matters is not size alone, but the unseen architecture of surface and substance. This was no ordinary comet. It was the first time in history that humanity could watch, in real time, an interstellar object come alive under our sun's influence. Each plume of gas was a revelation, each shift a dialogue between alien matter and our local star. For astronomers, it was a gift beyond measure. Unlike previous visitors that streaked past in days or weeks, Atlas promised months of observation, a drawn-out performance under the gaze of our most powerful telescopes and instruments. We could map its chemistry, track its pulse, and watch the choreography of its encounter with solar radiation. Yet fascination soon gave way to tension, for Atlas carried not only the mystery of its origins, but also a perilous destination. Its trajectory was leading it directly into the asteroid belt, a gauntlet littered with remnants of ancient worlds. Countless objects had been shattered there over eons. Now, for the first time, humanity would witness whether an interstellar voyager could survive the crossing, or whether its story would end among the rubble between Mars and Jupiter. Long before it reached the asteroid belt, the first signs of awakening began to ripple across 3I Atlas. Telescopes caught whispers of change, frozen ices, locked away for billions of years, stirring under the heat of our Sunday. At first, it was only a shimmer, a thin veil of gas and dust that clung to the nucleus like breath in winter air. But day by day, the glow expanded, forming a delicate coma. Soon, a faint tail extended outward, not unlike the ghostly outline of a traveler announcing its arrival to the solar stage. On the 27th of August 2025, the Gemini South Telescope captured color images of this transformation, the subtle hues revealing that these were not ordinary cometary gases. What we saw hinted at chemistry born under alien skies, forged in conditions far from anything familiar within our solar family. Measuring its body proved a puzzle. Estimates placed the nucleus somewhere between a few kilometers and over 10 kilometers across, larger than the enigmatic Oumuamua, yet still small enough to vanish inside a modern city's limits. But scale is deceptive in the cosmos. What matters is not size alone, but the unseen architecture of surface and substance. This was no ordinary comet. It was the first time in history that humanity could watch, in real time, an interstellar object come alive under our sun's influence. Each plume of gas was a revelation, each shift a dialogue between alien matter and our local star. For astronomers, it was a gift beyond measure. Unlike previous visitors that streaked past in days or weeks, Atlas promised months of observation, a drawn-out performance under the gaze of our most powerful telescopes and instruments. We could map its chemistry, track its pulse, and watch the choreography of its encounter with solar radiation. Yet fascination soon gave way to tension, for Atlas carried not only the mystery of its origins but also a perilous destination. Its trajectory was leading it directly into the asteroid belt, a gauntlet littered with remnants of ancient worlds. Countless objects had been shattered there over eons. Now, for the first time, humanity would witness whether an interstellar voyager could survive the crossing, or whether its story would end among the rubble between Mars and Jupiter. Red dwarfs, the quiet workhorses of our galaxy, dominate the thick disk population and offer a very different chemical stage for planet formation than the one we know around our Sunday. Their habitable zones, those fragile rings of possibility where liquid water might endure, huddle close to the star's faint warmth. The protoplanetary disks that once swirled around them carried temperature and pressure gradients, unlike those that shaped our Earth. With weaker ultraviolet radiation, these stars might preserve ices that would normally vanish, allowing exotic compounds to persist for eons. These ideas remain tantalizing hypotheses, waiting for the kind of confirmation only detailed spectroscopic studies can provide. And Atlas, drifting ever closer to its solar encounter, holds the promise of delivering that evidence. Adding to the intrigue are the polarimetric measurements, an astronomer's way of studying how light scatters off the dust of a comet's coma. In the case of Atlas, those studies revealed behavior unlike anything familiar from solar system comets. The polarization patterns hinted at differences in grain, size, texture, or composition, subtle fingerprints of a body that has wandered across interstellar gulfs for untold ages. Such details are not trivial. They whisper of how the comet formed, how its interior is structured, and what secrets of its native star system remain locked inside. Placing Atlas in context with its interstellar predecessors sharpens the contrast. 2I divided by Borisov, discovered in 2019, looked almost comfortingly familiar. Its chemistry, its outgassing, even its dusty coma, all closely matched the comets we know from home. It was alien, yes, but dressed in a disguise we could recognize. Oumuamua, by contrast, baffled us. It refused to show any comet-like behavior, flashing instead a mysterious, non-gravitational acceleration that continues to defy consensus. Some scientists now propose it may have been a shard from a Pluto-like world torn apart by stellar tides. Atlas stands somewhere in between, clearly a comet in its growing activity, yet marked by chemical signatures that betray its faraway origin. Familiar enough to interpret, alien enough to expand our cosmic imagination, it is precisely this tension that makes Atlas such a scientific treasure. Yet so much remains unknown. The exact size and shape of its nucleus elude us, blurred by distance and shrouded in dust. Its rotation period and the tilt of its axis are mysteries that will shape how evenly or chaotically it releases gas and ice into space. Beyond the basic detections of carbon dioxide and water, its full chemical inventory awaits more sensitive instruments. Most urgent of all, no one can yet say how Atlas will respond as the sun's heat intensifies. Will it flare spectacularly, shedding material in great streams? Or will it quietly disintegrate, erasing its secrets in a plume of dust? The coming months promised answers, and the astronomical community was mobilizing with rare coordination. The Hubble Space Telescope had scheduled a series of dedicated monitoring sessions. On Earth, the great 8 to 10-meter observatories were preparing to capture spectral fingerprints of changing chemistry. Even spacecraft scattered across the inner solar system were adjusting vantage points to provide multi-angled perspectives. Every observation would be unprecedented, the first close study of interstellar chemistry awakening under our sun, the first chance to monitor alien matter in real time, the first direct comparison of planetary building blocks forged in distant stellar nurseries. Atlas is not just another comet, it is a messenger from the ancient galaxy, carrying within its fragile body the chemistry of worlds we will never see. But before it can surrender those secrets, It must survive its passage through one of the most treacherous regions of space we know, the asteroid belt. For billions of years, that zone between Mars and Jupiter has harbored countless rocky sentinels, each on an orbit as predictable as it is perilous. To a fragile interstellar traveler racing through on a hyperbolic path, it is nothing less than a cosmic shooting gallery. And so the question becomes stark. Can Atlas endure long enough to tell us its story, or will survival itself become the greatest mystery of all? Between Mars and Jupiter stretches one of the most storied regions in astronomy. The asteroid belt. Popular imagination, stoked by decades of science fiction, envisions it as a lethal gauntlet, a swirling chaos of jagged rocks smashing together, spacecraft weaving desperately between tumbling boulders. On the silver screen, it is a place of peril and adrenaline, every second a near-death escape. Yet reality, as is so often the case in space, is both subtler and more compelling. Yes, the belt harbors millions of bodies, everything from the dwarf planet Ceres, nearly 1,000 kilometers across, down to grains of dust no larger than smoke. But the scale of the cosmos dwarfs them all. If Earth's orbit were a highway, the asteroid belt would resemble a lonely stretch where one might pass a single car only every few thousand kilometers. Distances between major asteroids are measured not in meters or even kilometers, but in millions of kilometers. NASA probes have slipped through this domain many times, never once striking a rock, a testament to the vastness that hides within what seems crowded. And yet, for 3I Atlas, the journey is anything but ordinary. The vast majority of asteroids travel the sun's path in prograde motion, circling in the same direction as the planets. Atlas, however, cuts across their ranks on a retrograde orbit, tilted nearly 175 degrees against the ecliptic plane. In human terms, it is like speeding the wrong way down a one-way highway. The odds of a meeting remain infinitesimal, but the stakes are higher. Any collision will not be a gentle nudge but a catastrophic impact, as objects slam together at tens of kilometers per second velocities that turn even modest fragments into cosmic bullets. In such encounters, survival is rare, destruction almost guaranteed. The asteroid belt itself is not a uniform sea of rubble, but a layered, evolving archive of the early solar system. Its densest swaths lie close to the ecliptic, and Atlas's trajectory slices directly through that heart, rather than coasting safely above or below. Among its residents are worlds with names that carry weight in astronomy: Ceres, Vesta, Pallas, Hygeia, giant survivors of a chaotic youth, still round and geologically complex. Around them drift countless irregular shards, the broken bones of larger worlds shattered by billions of years of collision. They are not all alike. Some, the carbon-rich C-types, are dark relics of the outer solar nebula, still carrying primitive material largely unaltered since the dawn of planets. Others, the silicate-bright S-types, are the debris of differentiated bodies that once melted and resolidified, their rocky crusts scattered. Rarest of all, the M-types gleam with nearly pure metal, perhaps the stripped cores of ancient planetoids long since destroyed. A few interlopers have origins far beyond immigrants, hurled inward by the migration of giant planets, preserved fossils of a wider solar system. For Atlas, slicing through this cosmic museum, each category is not simply an object of scientific curiosity, but a potential threat, a chance meeting with an alien messenger or a fatal stone. Ironically, the greatest dangers do not come from the large, charted bodies, but from the legions of fragments that slip beneath the gaze of telescopes, pebbles, boulders, shards drifting invisibly through the void. These, too small to track, too numerous to avoid, form a hidden hazard zone. Even smaller still, the dust must be reckoned with, motes of matter that seem harmless until multiplied by speed. At interstellar velocities, even grains can bite like bullets, carving scars into metal or rock. For Atlas, an object born far from here, the asteroid belt is not a static region of science fiction drama, but a true crucible, vast, mostly empty, but never without risk. Across the asteroid belt, the space between Mars and Jupiter is thick with fine debris. Dust particles, ranging in size from micrometers to millimeters, are constantly born from collisions between larger rocks and slowly spiral toward the Sun, tugged by radiation pressure. For a comet like 3I divided by Atlas, alive with a growing coma and a luminous tail, this region is less a quiet void and more a sandblasting arena. Each grain of dust, striking at cosmic speeds, has the potential to chip away at its surface, reshaping its appearance as it drifts forward. Yet the story is not only about erosion, it is about electricity and magnetism as well. These charged grains dance with the solar wind, bending under invisible electromagnetic forces, creating waves and instabilities that ripple outward through Atlas's expanding halo. The result is not a simple path, but a chaotic ballet driven by gravity, radiation, and plasma, a three-body system where prediction gives way to turbulence. And still, the paradox remains. Despite the hazards, the odds of a catastrophic collision are vanishingly small. NASA's models show the asteroid belt to be far emptier than the cinematic visions of crowded space highways. It is more like a vast ocean dotted with scattered islands, and the chance of striking one is negligible. But negligible is not zero. For an interstellar traveler carrying the weight of scientific dreams, even small risks loom large. A micro-impact might trigger a sudden burst of activity, briefly brightening the comet or reshaping its coma. Streams of dust concentrated in patches of the belt could imprint themselves on its tail, temporary scars that double as scientific clues, revealing both the local environment and the shifting moods of the solar wind. For astronomers, this passage is less about survival and more about discovery. It is the rare opportunity to watch an object from another star system navigate our own debris field. Wide-field surveys stand ready to capture its progress, frame by frame, as it cuts across different regions of the belt. Solar observatories will compare disruptions in its tail with the prevailing gusts of charged particles from our star, disentangling local interactions from the larger weather of the heliosphere. Questions ripple forward. Will Atlas reveal subtle changes in activity as it meets different dust densities? Can its crossing help map unseen particle populations adrift between the major asteroids? Most provocatively, how will its alien chemistry, the frozen signature of another sun, react to the peculiar conditions of our belt? The drama is not one of doom but of exploration. For the first time, humanity witnesses such a crossing, turning our solar system into a vast laboratory where an interstellar relic becomes the test subject. As telescopes align and instruments calibrate across the globe, Atlas sails into the belt. Not the perilous gauntlet imagined by Hollywood, nor the perfectly safe emptiness implied by numbers, but something richer, a proving ground. Here, an ancient wanderer faces its greatest trial since entering our skies, while we, its observers, stand ready to learn. It began almost invisibly, a faint shift only the most attentive eyes could perceive, as 3I Atlas crept closer to our Sunday. At first, it was nothing but a wandering point of light against the fixed tapestry of stars, its motion so subtle that only careful comparison revealed its passage. Yet with every day of approach, solar energy reached deeper into its ancient core, stirring materials that had lain dormant for billions of years. Slowly, ices buried since the dawn of its formation awoke, sublimating directly into gas. These escaping vapors dragged dust into space, building a tenuous shroud around the nucleus. Astronomers call it a coma, but in practice, it is an ephemeral world, sometimes larger than a planet, transforming what was once a dark relic into a luminous spectacle. But Atlas was no ordinary comet. Instruments aboard the James Webb Space Telescope captured its outgassing in exquisite infrared detail and revealed something profoundly strange. Carbon dioxide dominated the early release. In most comets of our solar family, water vapor announces the beginning of activity, with carbon dioxide rising later and farther from the sunday. Atlas was breaking that script. It was active at distances where most comets remain silent. Was its surface built from volatile ices unusually rich in carbon dioxide, or was some hidden process heating it from within? Either answer set it apart from the native citizens of our solar system. As the coma swelled, the sun's radiation sculpted it into forms more intricate. Each photon carries momentum, and when it scatters off dust, it imparts a steady push. Meanwhile, the solar wind, an endless stream of charged particles, ionized gases, and swept them into vast filaments. These twin forces carved Atlas's dual-tail signature, one broad and curved with reflective dust, the other razor, straight, a plasma streamer pointing away from the sun regardless of the comet's path. These tails were magnificent, but also tragic. Every grain of dust, every molecule of gas torn away, was a fragment of interstellar history material that had voyaged across light years only to dissolve under our star's glare. The plasma tail revealed even deeper drama. When the solar wind collides with cometary ions, energy and momentum shift in turbulent waves. The comet becomes a probe of space weather, its tail bending, disconnecting, and rebuilding in response to flares and storms launched from the sunday. Coronal mass ejections can twist it into knots, even sever it completely, only for it to reform as the violence subsides. For Atlas, with its carbon dioxide, rich chemistry, the plasma played by new rules. These ions responded differently than those of water, hinting at exotic instabilities, phenomena unrecorded in any comet we had studied before. What began as a mere point of light had become a laboratory, a warning sign, and a tale in the making. In its fragile tale, we could read both the beauty of cosmic renewal and the ticking erosion of something irreplaceable, a visitor dissolving even as it revealed its secrets. The tale of 3I divided by Atlas was not merely a spectacle unfolding against the black canvas of space. It was a living experiment, a natural laboratory where plasma physics played out under conditions no human machine could ever reproduce on Earth. Yet, amid the shimmering glow of its expanding veil, astronomers noticed details that stirred unease. The activity was uneven, jets of gas and dust erupting asymmetrically across the nucleus. Such lopsided outgassing hinted at deeper complexities. Volatile patches exposed to sunlight, hidden structural weaknesses, or subtle chemical layering locked within its ancient body. These asymmetries carried consequences. The escaping gases did not just illuminate the comet, they pushed against it, imparting torques capable of altering its spin. A slight imbalance today could cascade into violent tumbling tomorrow, even catastrophic fragmentation. What looked like beauty from afar was, in truth, a drama of stress. This nucleus had already endured 4 billion years of bombardment by cosmic rays, of freezing and thawing through interstellar nights. And now, under the relentless heat of our sun, it was straining to hold together. Observations told the story with increasing urgency. Brightness curves did not rise smoothly, but flickered and leapt, evidence of sudden outbursts rather than gentle release. High-resolution images sharpened the view. Narrow jets piercing the coma, localized vents screaming matter into space, reshaping the shroud around the nucleus into ever more complex forms. Any single feature might be dismissed as ordinary cometary behavior, but together they trace the portrait of an object unusually restless, reacting to solar warmth with a volatility unfamiliar even to seasoned observers. This instability could not have chosen a worse moment. Atlas was steering toward the asteroid belt, the solar system's most treacherous gauntlet, dense with debris and the gravitational influences of massive worlds. A fragile nucleus, already cracking under internal pressures, faced added peril from collisions and perturbations. Yet in this tension lay science of immense value. Every spectral line in its glow, every flare of brightness, every shifting filament of its tail offered humanity a chance to probe alien chemistry, to learn how materials forged in distant stars behave under the sun's embrace. And so, astronomers found themselves caught between dread and exhilaration. Was Atlas simply revealing the natural behavior of matter, untouched since its birth in another star's nursery? Or was it announcing its own impending collapse? Its chemical fingerprints spoke of a heritage unlike anything native to our skies. Its patterns of activity defied neat comparison to comets we thought we understood. Ahead lay the asteroid belt, transformed from a celestial landmark into a proving ground, a crucible where this interstellar wanderer would either survive long enough to share its secrets or break apart and vanish into dust. The brightening of Atlas was not just a sign of awakening. It was the beginning of vulnerability, a fragile flare in the darkness. Something ancient was stirring at the edge of our solar system, and for the first time, we were watching closely enough to discover what such a visitor was truly made of. Atlas is not the first wanderer from beyond our solar system to pass across our telescopes, and looking back at its predecessors helps us measure both our hopes and our cautions. Each of these rare interstellar visitors has arrived bearing its own strangeness, its own riddles, and, ultimately, its own lessons about the vast diversity of worlds drifting in the galactic dark. The first confirmed interstellar object, 1I Oumuamua, blazed into scientific and public attention in October 2017. Detected by the Pan-STARRS survey in Hawaii, it was given a name that means messenger, from afar, arriving first. Few titles could have been more fitting. Oumuamua shattered every expectation. It was stretched to an extreme 10 times longer than its width, something unlike any natural body astronomers had ever catalogued. Some even whispered that it might not be natural at all. Stranger still, as it passed within Earth's orbit, no glowing tail, no hazy coma betrayed its presence. Here was an object behaving like no comet ever observed. Then the anomaly deepened. As Oumuamua sped away, it began to accelerate in a subtle but undeniable way, motion not fully explained by the pull of the Sunday. Outgassing seemed the obvious culprit, yet no dust or vapor could be seen. Calculations suggested water ice sublimation might provide the needed push, but only at levels too faint for our instruments to catch. Explanations proliferated. Perhaps it was a shard of a Pluto-sized body torn apart in a stellar encounter, its form sculpted by catastrophe. Or maybe it was a slab of hydrogen ice, quietly evaporating into invisibility across the interstellar void. Whatever the truth, Oumuamua left behind more questions than answers. 2 years later, the cosmos offered a second messenger, 2I Borisov, spotted by amateur astronomer Gennady Borisov in August 2019. This visitor felt comfortingly familiar. It wore a bright coma, grew a tail, and revealed the spectral fingerprints of water vapor, carbon monoxide, and hydrocarbons. In short, Borisov behaved just as one would expect a comet to behave, even if its birthplace lay around another star. Its nucleus endured, its activity followed predictable models, and its chemistry mirrored that of comets born in our own Oort cloud. If Oumuamua was the eccentric stranger, Borisov was the reassuring cousin alien, yet recognizably kin. Now comes Atlas, and it seems to straddle these two legacies. Like Borisov, it has grown its coma and tail, proving its cometary nature. Yet like Oumuamua, it teases with mysteries, chemical and physical properties that defy our neat categories of comet behavior. Its very path adds to the drama. Whereas Oumuamua shot through on a steep, clean trajectory, and Borisov skimmed nearer the sun without entering chaos, Atlas has chosen the most perilous stage. On a retrograde course along the ecliptic itself, it plunges straight through the asteroid belt, a gauntlet of stone and shadow. And as if to remind us of how unpredictable these cosmic wanderers can be, we need only recall the brilliance of Comet C 2023A3 Suchinshan Atlas, which dazzled the skies in 2024. Against that backdrop, Atlas arrives not as an isolated oddity, but as the newest chapter in a growing saga of interstellar visitors, each rewriting, in its own way, our understanding of the galactic traffic that brushes past our small and fragile world. In the chronicles of celestial wanderers, few have given us such a vivid lesson in cometary behavior as one particular solar system comet. Against all odds, it swept past the sun, blossomed magnificent tails, and endured the fiery embrace of a close solar passage. Its dance with coronal mass ejections, captured in exquisite detail by the SOHO spacecraft, revealed how magnetic reconnection events could tear apart and rebuild cometary tails in dramatic fashion. What seemed like destruction was, in truth, part of the comet's natural cycle. Hundreds of such disruptions have been documented, reminding us that broken, reformed tails are not omens of doom, but signatures of resilience. From these precedents we may draw cautious hope. Atlas too might endure the chaos of solar wind assaults. Yet the distinction is vital. While comets regularly bear scars from solar encounters, they do not ignite the sun's tempests. The supposed link between their passages and solar upheavals belongs more to folklore than science. Still, Atlas compels attention for reasons beyond survival. Unlike its predecessors, it carries chemistry that is unmistakably foreign. Borisov echoed the traits of local comets. Oumuamua, enigmatic, left no clear chemical trail. Atlas, however, sings in spectra of alien resonance. Its coma, rich in carbon dioxide, displays a chemistry absent among our well-studied kin, hinting at birthplaces under alien stars, in conditions unfamiliar to our own cosmic nursery. The fortune of observation is also on our side. Oumuamua arrived already leaving, a guest glimpsed only in retreat. Borisov lingered longer, yet faint and elusive. Atlas, by contrast, offers us time years of tracking across vast distances. Every stage of its solar encounter can be followed, catalogued, and compared. The era of coordination has advanced as well. NASA, ESA, NULAB, and observatories across the globe weave their efforts together, supported by a tireless chorus of amateur astronomers. No night passes without eyes upon it. Data now moves at the speed of light across networks, weather and scheduling no longer dictating the fate of discovery. Technology itself has become an ally. Machine learning scours images for subtle morphological shifts the human eye might overlook. Spectrographs now pierce deeper, detecting molecules at whispering concentrations. Simulations of dust and plasma reveal layers of complexity once hidden. And yet, for all our advantages, Atlas sails into hazards its forebears never faced. Neither Oumuamua nor Borisov threaded the crowded corridors of the asteroid belt while their comae bloomed. Neither endured the tangled web of gravitational and electromagnetic forces that now await Atlas. History offers guidance but not certainty. Interstellar visitors have survived their passages, True, yet each has carried mysteries that defied expectation. Atlas may follow their script, or it may astonish us with entirely new phenomena. What lies ahead is the most perilous chapter of its voyage, a crossing through the dense heart of our solar neighborhood. There, amid drifting stones and magnetic tempests, its billion-year journey will meet a crucible. Whether it emerges whole or fractured, Atlas will inscribe its testimony across our skies. In its light and dust may reside answers seeded long before humanity's first breath, fragments of a story older than Earth itself, now unfolding before our eyes. To grasp the journey of 3i Atlas, one must think beyond the flat diagrams often used to illustrate the solar system. Its path is a lesson in orbital mechanics, the kind of challenge that could test even the most seasoned spacecraft navigators. Most bodies in our celestial neighborhood trace gentle arcs in roughly the same direction, preserving the angular momentum imparted during the solar system's birth. Atlas, however, is the rebel. It cuts against the grain, flying not with the planets but against them, on what astronomers call a retrograde orbit. With an inclination of nearly 175 degrees, it moves almost exactly opposite to the prevailing traffic. Imagine a lone vehicle racing west, while every other car speeds east on a crowded expressway that is Atlas in the asteroid belt. This reversal is more than eccentricity. In space, collisions are governed by kinetic energy, and that energy depends on the square of relative velocity. Two objects, nudging in the same direction, exchange little force, but a head-on encounter between opposing travelers releases energy of an entirely different order: violent, catastrophic, unrelenting. For Atlas, threading through the asteroid belt in reverse means any impact, however remote the odds, would carry devastating consequences. Its approach to the inner solar system carries drama of its own. First glimpsed from the direction of Sagittarius, it began as a wraith of magnitude 16 to 18, barely distinguishable through the lenses of professional observatories. From a distance of 3 to 5 astronomical units in July, it surged inward, skimming the main asteroid belt on its way to a closest solar approach of 1.357 AU by late October 2025. The geometry of its trajectory is a celestial gauntlet, not only a narrow threading through rocky hazards, but a shifting target for Earth's telescopes. During its July and August passage through Sagittarius and Ophiuchus, Atlas demanded patience, large mirrors, precise tracking, and long exposures. With time, its increasing activity will brighten the object, bringing it within reach of smaller instruments. Yet the speed of its movement across the sky ensures the chase will remain demanding, as astronomers struggle to keep pace with this cosmic fugitive. Its near misses with planets add another layer of spectacle. On the 3rd of October 2025, Atlas will pass within 0.19 AU of Mars, about 28 million kilometers, a vast gulf by terrestrial standards, but near enough that spacecraft orbiting the red planet may capture privileged views. Other encounters follow: 0.65 AU from Venus on November 3 and 0.36 AU from Jupiter on the 16th of March 2026. None will tug Atlas off its hyperbolic course. Its speed is far too great for any gravitational leash. Yet each close pass offers a chance to refine trajectory models, triangulate its position, and study it from multiple vantage points scattered across the solar system. For Earth, there is no peril. In December 2025, Atlas will sweep past at a minimum of 1.8 AU, 270 million kilometers farther than Mars ever strays from us. Even if it were to shatter entirely, the debris would remain chained to the same outbound hyperbolic arc, slipping past our world without consequence. And still, The numbers defy comprehension. Its hyperbolic excess velocity, its resting speed in the interstellar dark registers around 58 kilometers per second. As it plunges toward the Sun, gravity whips it faster still, pushing relative velocities with belt objects past 100 kilometers per second. To grasp this, consider the fastest craft built by human hands. NASA's Parker Solar Probe, a sliver of engineering hurled sunward, peaks near 190 kilometers per second at perihelion. Atlas moves in the same league, not by design, but by the raw inheritance of cosmic momentum. In its furious trajectory, we witness both the fragility and resilience of an ancient traveler, an interstellar wanderer threading its way through a gauntlet of stone. Atlas moves with a velocity that rivals the limits of our finest propulsion systems, yet this pace is not new to it. It has likely been sustained for millions, if not billions, of years. Its chosen path, a retrograde trajectory skimming near the ecliptic plane, ensures maximum exposure to the turbulent currents of the solar wind. This is no mere coincidence. The ecliptic is a crowded stage, home to the densest field of asteroids and dust, as well as the most intricate electromagnetic theater our star can produce. Coronal mass ejections erupt from the solar surface, co-rotating interaction regions spiral outward, and a constant gale of charged particles sweeps across this invisible highway. Atlas, by plunging directly through it, becomes both traveler and test subject. For heliophysicists, the comet's passage is nothing short of a cosmic gift. Never before has an interstellar object threaded such a course, offering a chance to watch in real time how alien ices and dust respond to solar wind phenomena. With spacecraft stationed across the inner solar system, scientists can capture the same event from multiple vantage points, stitching together stereo perspectives that reveal a three-dimensional truth impossible to glean from Earth alone. Ground-based telescopes, too, benefit from this geometry. Unlike its brief-lived predecessors, objects that cut in from high inclinations, flashing across our skies for mere weeks, Atlas lingers. Month after month it remains within sight, allowing astronomers across both hemispheres to take turns under shifting seasons, to retry under clear skies when weather fails, and to return again and again to verify strange or unexpected signals. The scientific fortune of this orbit lies not just in visibility, but in variety. Each leg of its journey through the solar system presents a new laboratory. In July and August, Atlas moved through the outskirts of the asteroid belt, a comparatively quiet region where the comet displayed its baseline behavior, relatively untouched by solar wind turbulence. September drew it into the main belt itself, where solar heating grew stronger and interactions with drifting dust and massive asteroids introduced new stresses. Soon, October and November will hurl it toward the inner system, where radiation sharpens, the solar wind roars louder, and the true trial begins. Can its nucleus endure blistering heat and relentless bombardment without fracturing into silence? Even its retrograde orbit carries advantages. Against the slow march of background stars, Atlas streaks with exaggerated speed, making it easier for observers to pick out, track, and study with precision. This rapid drift reduces contamination in spectral readings and sharpens the accuracy of positional data, a small but vital boon when chasing a fleeting interstellar guest. Now, as Atlas plunges toward its October perihelion, the stakes rise with every kilometer. The asteroid belt grows denser, the risks greater. Its path is not merely a route but a crucible, a gauntlet carved by gravity and chance, testing whether this relic from beyond our stars can outlast the dangers that have undone countless smaller bodies. In its trajectory we find both the rigor of orbital mechanics and the artistry of drama, a natural experiment scripted across the heavens. And there we sit, on the fragile world it now visits, watching as an ancient traveler threads the needle through the most perilous arena of our solar system. The asteroid belt has always carried an outsized reputation in our collective imagination, a gauntlet of tumbling rocks, a place where danger lurks in every direction. In reality, it is both less threatening and more fascinating than the stories suggest. Here dwell some of the most iconic worlds of the inner solar system. Ceres, nearly 1,000 kilometers across and rounded into the dignity of a dwarf planet. Vesta, its battered face etched with scars of colossal impacts. Pallas and Hygeia, giants in their own right, whose gravity herds smaller fragments into long-lived families. They are the ancient titans of this region, remnants of planetary beginnings, shaping the belt's architecture for billions of years. Yet for Atlas, an interstellar comet barreling through on a hyperbolic trajectory, even these immense bodies offer little real threat. Space is so unfathomably vast that the odds of a direct hit verge on the absurd. NASA's probability studies reinforce the comfort. Spacecraft from Pioneer 10 to the latest Mars missions have threaded this region without encountering anything larger than dust motes. If Earth were a marble placed in New York, the nearest asteroid might be another marble resting in Los Angeles. The distances swallow the danger. But Atlas is not like our spacecraft. Its retrograde orbit pitches it headlong against the solar system's prevailing traffic, and in such meetings, velocity becomes everything. Relative speeds can climb above 100 kilometers per second, and in physics, speed is power squared. A collision under these conditions would be catastrophic. Imagine even a pebble, accelerated to such violence, striking with the fury of a nuclear blast. Larger fragments would not merely bruise Atlas, they would obliterate it, scattering its nucleus into a storm of fragments. From Earth's telescopes, we would see a sudden bright flash, a brief flare of destruction, followed by the dispersal of a ghostly cloud as pieces of the visitor tumbled outward, each carving its own lonely path back into interstellar night. The alien chemistry locked within this one fragile body would vanish with it, lost to untrackable debris. Such a vision stirs both scientific fascination and public dread. Whenever collisions in space make the headlines, imaginations leap to disaster scenarios. Could fragments veer toward Earth? Could Jupiter's gravity bend trajectories into our path? The mechanics answer decisively, no. Atlas races on a hyperbolic orbit, carrying far too much energy to be trapped or redirected by any planet. Even mighty Jupiter cannot haul it into line. Should a collision splinter it, the fragments would inherit that same excess of energy, continuing outward into the dark between stars, never to return. Earth is safe, though the price would be the irreversible loss of a messenger from beyond. If danger exists, it lies not with the famous asteroids, but with the countless smaller fragments, the unseen multitude, from fist-sized rocks to car-sized boulders, drifting in their quiet orbits. These are abundant enough to present a real hazard. Atlas's solid nucleus may measure only a few kilometers across, but as it nears the sun, sublimating ice releases plumes of dust and gas, unfurling a coma that can span hundreds of thousands of kilometers. This vast, diffuse envelope becomes a vulnerable target. While tiny particles cannot destroy Atlas, they may strike the coma and trigger cascades, localized outbursts, sudden jets, rippling distortions in the comet's luminous tail. To astronomers, these would be signposts, observable signatures of invisible collisions. A sudden brightening, a shift in tail structure, an asymmetric jet of dust could all whisper of impacts with belt material, turning Atlas into both traveler and instrument, probing the density of small debris that science has scarcely mapped. Even the great asteroids exert subtler hazards, not by collision but by gravity. As Atlas flies past, their pull may perturb its coma, or stretch its tail, introducing complexities to its already turbulent behavior. Such interactions are delicate, not catastrophic, but they enrich the scientific harvest. Every flicker of brightness, every sudden jet, every change in morphology would be a note in the evolving symphony of Atlas's passage, a natural experiment conducted in real time, where a relic of deep space reveals its fragility against the quiet minefield of our solar neighborhood. In this way, collision scenarios stretch beyond mere survival odds. They remind us that the asteroid belt is not an arena of certain doom, but a stage where chance encounters, however unlikely, play out with staggering consequence. For Atlas, the journey is peril itself, not because space is crowded, but because it is unforgiving. A single mote, a grain of stone in the void, could determine whether we continue to watch a comet blaze across the inner solar system, or instead witness its sudden death, a spark extinguished against the immensity of space. Though a direct strike with planetary bodies like Ceres or Vesta is practically ruled out, the gravitational tides of these giants could still whisper upon 3i Atlas, altering its fate in ways less visible but no less profound. Such encounters would never hurl it earthward, but they might nudge its spin into a faster rhythm, tilt its rotational axis, or strain its brittle skeleton until cracks began to creep inward. In those subtle stresses lies the possibility of fragmentation, an ancient wanderer undone, not by a crash, but by the silent hand of gravity. The asteroid belt itself is far from a monolithic native population. Scattered among its residents are immigrants, bodies forged in distant provinces of the solar system, and exiled here by the sweeping migrations of planets long ago. Some carry the same cold chemistry that defines Atlas, perhaps laden with carbon dioxide ices born in the outer dark. A meeting between this interstellar traveler and one of those displaced kin would be more than chance. It would be a dialogue across epochs, revealing how conditions of birth echo across stellar neighborhoods. Among the milestones of this passage, October 3rd stands out. On that date, Atlas will brush past Mars at 0.19 astronomical units, a cosmic near-miss that offers scientists a perfect vantage point. From their orbits, Mars's spacecraft will be able to scrutinize the interloper in unprecedented detail, close enough to extract data, yet far enough to avoid the tug of disruptive gravity. It is the kind of compromise astronomers dream of, proximity without peril. Yet the wider gauntlet remains the asteroid belt itself. In popular imagery, it glimmers as a dense field of boulders, a minefield awaiting trespassers. The truth, shaped by celestial mechanics, is more forgiving. Vast distances stretch between the rocks, making the odds of survival overwhelmingly favorable. Day by day, as Atlas sails unscathed through this imagined chaos, confidence swells that it will emerge intact, carrying its ancient cargo toward the Sunday. And yet, the tiniest chance of ruin lingers. Each fluctuation in brightness, each faint distortion in its outline, hints at unseen collisions with dust or pebbles. It is this razor-thin edge between assured survival and sudden erasure that lends drama to every observation. Space, after all, is no sanctuary. It is a battlefield of energies vast enough to unmake worlds. Should Atlas be shattered by fragments born of our own system's creation, the irony would be haunting. But for now, probability bends towards survival, and with it the promise that this alien relic may one day tell us secrets older than the sun itself. As Atlas grows brighter, its once solid nucleus is no longer just a lump of rock and ice. It is becoming a vast natural experiment, a plasma chamber on a cosmic scale. Here, in the vacuum between worlds, forces that shape the universe itself are playing out in plain sight. Ultraviolet light from the sun strikes the gases streaming off the nucleus, carbon dioxide and water vapor, the main ingredients of its coma, stripping them of electrons and leaving behind a cloud of charged particles. This is plasma, matter in its most electric and volatile form, no longer passive but reactive, sensitive to invisible magnetic fields that swirl and ripple through space. And the stage it enters is alive with energy. The solar wind, a torrent of charged particles racing outward from the sun at hundreds of kilometers per second, does not flow lazily past comets as water does around stones. When it meets a comet's plasma envelope, the two environments begin to speak. Freshly born ions from Atlas are snatched up by the magnetic field carried within the solar wind and flung along at high speeds. Physicists call this mass loading, like throwing sandbags into a rushing current. The flow slows, bends, and reshapes itself. At Comet 67P, the Rosetta spacecraft recorded the solar wind deflected by more than 45 degrees, twisted into spirals of magnetic turbulence. Around Atlas, the story may be even stranger. Its carbon dioxide ions do not behave like the water ions so familiar to cometary studies. Their different mass and charge could spawn plasma phenomena never before witnessed. Waves ripple through this environment, magnetosonic pulses, alpha waves, exotic oscillations that can travel faster than the plasma itself, announcing the comet's presence to the solar wind like a beacon before its matter even arrives. For Atlas, the drama intensifies. On its retrograde path through the asteroid belt, it meets the solar wind head-on at enormous relative speeds, generating sharper shocks and stronger wave signatures. Its near-ecliptic orbit exposes it fully to the sun's most turbulent winds. The comet's plasma tail becomes a windsock stretched across millions of kilometers, its structure whispering secrets about solar storms we cannot measure from Earth. When a coronal mass ejection barrels through space, the tail responds instantly, writhing, twisting, sometimes even tearing away entirely. In spectacular disconnection events, whole sections of the tail detach and drift off, while new streams of plasma grow behind the nucleus, ready to be torn away again. Time-lapse photographs have caught these moments in other comets' tails ripped from their anchor, wriggling like luminous serpents in the dark. For Atlas, whose chemistry is rich in carbon dioxide, such interactions could be especially dramatic, painting the solar wind with a palette of effects no telescope has seen before. It is not simply a comet anymore. It is a stage where the invisible powers of plasma physics reveal themselves in full electric theater. In the realm of space, even the smallest particle can rewrite the fate of a wandering world. Around 3I Atlas, carbon dioxide ions trace wide spirals, while water vapor ions curl along tighter paths. These subtle differences in gyroradii may seem like footnotes in plasma physics, yet they shape the comet's tail into strange and unstable architectures no telescope has ever seen before. Here, turbulence becomes a teacher, revealing how charged gases behave under stresses beyond any earthly laboratory. Surrounding the nucleus, the coma is not a quiet halo of dust. Every grain is alive with charge, struck by ultraviolet light from the sun, by the constant wash of plasma, and by the restless departure of secondary electrons. Gravity and radiation alone no longer rule. Instead, invisible electric and magnetic fields tug at the grains, choreographing a restless ballet that veers between order and chaos. Experiments on Earth hint at the wonders of such dusty plasmas, waves, instabilities, and collective murmurs, but Atlas magnifies these effects onto scales that leap from micrometers to millions of kilometers, weaving atomic physics and astrophysics into a single theater. As the comet threads deeper into the ecliptic plane, it confronts the sun's most complex moods. Here lie the shifting borders of magnetic polarity, the crash sites where fast solar wind collides with slow, and the violent intrusions of coronal mass ejections. Each encounter reshapes the comet's luminous anatomy. A boundary crossing can twist the tail in an instant. Interaction regions squeeze the coma, stirring waves like drums in deep space, and a solar storm can sever the tail outright, snapping it like a banner in hurricane winds. We are not blind to this drama. A fleet of spacecraft, the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, the Parker Solar Probe, and the silent watchers circling Mars stand ready to capture these symphonies of plasma from multiple angles. Together, they form a three-dimensional map of an interstellar body's struggle against the breath of our star, a record that no earthbound lens could ever compose. The implications surge far beyond cometary law. The same principles govern stellar atmospheres, planetary shields, and the restless tides of the interstellar medium. By accident of its trajectory, Atlas has become a probe, a messenger carrying not just dust and gas, but lessons written in electromagnetic language. Its glowing tail broadcasts alien chemistry into the spectrum, each photon a clue to its birth in another sun's cradle. With every kilometer, the tension mounts. The coma swells, feeding more ions into the solar wind's furnace. Radiation grows harsher, chemistry more violent. Fields bend and twist, stressing the fragile nucleus. These forces may cradle the comet, holding it together, or they may pry it apart from within. The verdict depends on equations of plasma physics still only half understood. One truth is clear: Atlas is no longer merely a comet. It is a cosmic experiment in motion, a 4-billion-year-old archive of matter subjected to the crucible of a solar system it did not know. Whether it survives or splinters, it leaves behind revelations that bind the scale of atoms to the architecture of galaxies. Hidden dangers rarely announce themselves with cinematic explosions. While astronomers often picture 3I Atlas smashing into a mountain-sized asteroid, the truer threat is quieter, almost invisible, and far more insidious. The space between Mars and Jupiter is no tranquil void. Instead, it is laced with uncountable fragments, dust grains, no larger than specks of smoke, pebbles adrift in darkness, shards that together form a ceaseless storm. Moving at tens of kilometers per second, each particle becomes a microscopic bullet, a sandblasting rain that eats away at whatever dares to cross its path. For Atlas, these micro-impacts are not the cinematic deathblow of a single collision, but a constant gnawing. Each strike carries kinetic energy magnified by velocity, sputtering away atoms and molecules from its surface. Over millions of years, this process space weathering has sculpted moons, asteroids, and comets. Surfaces darken, chemistry shifts, and tiny glassy beads are forged in the violence of impact. For an interstellar relic, whose crust may hold secrets from before the birth of the sun, this weathering is both threat and opportunity. Destructive as it is, it can also strip away radiation-darkened veneers, exposing fresher material beneath. Some of the sudden bright flares and narrow jets we now glimpse from Earth may be nothing more than hidden layers awakened by a speck of dust. Thermal stress compounds the danger. As Atlas draws nearer to the sun, the contrast between searing exterior and frozen core sets up a battlefield of pressure. Rock expands, cracks form, fissures split open, and volatile ices escape in violent bursts. These outgassing events are the fireworks of comets, breathtaking to watch, but devastating to structural integrity. We have seen this story before. Comet C 2019Y4, also named Atlas, flared into brilliance in 2020, only to fragment into ghostly shards under the combined strain of solar heat and its own fragility. Comet Ison, once hailed as the comet of the century, suffered a similar fate in 2013, unraveling into a cloud of dust as tidal forces and sunlight tore it apart at perihelion. So Atlas journeys on, not through empty space but through a gauntlet of dust, heat, and hidden violence. Its survival is a balancing act, eroded but revealed, cracked but illuminated, fragile yet luminous. Every moment it persists, it writes a new page in the story of cosmic endurance, and every moment it might still fall apart, scattering its secrets back into the dark. The puzzle surrounding 3I Atlas is not just about where it came from, but about how long it can endure. The James Webb Space Telescope has detected a chemistry rich in carbon dioxide, and that alone complicates predictions. Such a signature might hint at a hardened, radiation-baked crust capable of resisting solar punishment, or it could betray a fragile, volatile interior waiting to fracture under stress. We have seen both possibilities among comets born of our own solar system, and yet, when the subject is an interstellar wanderer, precedent becomes less a guide and more a warning of uncertainty. Age itself plays a dual role. If Atlas is older than our solar system, then its endurance so far is nothing short of astonishing, surviving billions of years of cosmic ray bombardment and countless thermal cycles suggests either remarkable toughness or an uncanny stability in composition. But longevity can carry a hidden cost. Layers hardened by time may be brittle, and what has survived the silent dark of interstellar space might prove ill, prepared for the furnace of solar approach. The first cracks may already be showing. Atlas has brightened, not smoothly, but erratically. Jets fire in sudden bursts, the coma thickens and thins in irregular rhythm. These signatures whisper of internal stress vents opening under thermal expansion, fissures carving their way outward, or perhaps the earliest notes of structural failure. To catch these moments, astronomers have mobilized the sharpest eyes we possess. Hubble, alongside Earth's adaptive optics systems, is tasked with resolving even the subtlest deformations elongated brightness cause, hints of fragmentation, the appearance of multiple nuclei slipping free of one another. Each image becomes a diagnostic scan of a body under duress. But the threat is not purely internal. As Atlas plunges into the asteroid belt, it enters a dust ocean invisible to the naked eye. Each grain, no bigger than sand, strikes at hypervelocity. Individually, they are trivial. Collectively, they are relentless. The comet's coma, billowing outward like a vast parachute, becomes a target. Impacts trigger sparks of heat, pockets of sublimation, new jets erupting unpredictably. With Atlas's peculiar chemistry, the danger magnifies. Unlike water ice, carbon dioxide vaporizes at lower temperatures. A dust impact that would merely scuff a normal comet could, for Atlas, unleash explosive outbursts. The environment it now faces is textured and uneven. Dust bands, zodiacal clouds, trails of ancient asteroid collisions all form a shifting backdrop through which Atlas sails. Each region it crosses may alter its brightness, bend its tail, and leave behind a coded record of how interstellar chemistry reacts to a solar system gauntlet. For scientists, even destructive events have value. Should Atlas fragment, its innermost layers will scatter across its coma, exposed to telescopic scrutiny. In this sense, asteroid belt dust becomes nature's probe, drilling samples from depths we could never otherwise reach. Yet timing is everything. Each week that Atlas survives intact yields extraordinary dividends. Longer monitoring, higher resolution measurements, a more complete chronicle of how an alien body transforms under solar influence. But each week also increases the risk. The belt's densest regions swarm with larger fragments, and one decisive strike could end the story in an instant. This passage marks uncharted territory. Neither Oumuamua nor Borisov ventured so deeply into particle-rich environments, and both remained relatively inert. Atlas is the first interstellar comet to blaze through the asteroid belt with a living coma. Its survival uncertain, its reactions unpredictable. Every observation now matters. Every brightness curve might be the last glimpse of an intact nucleus before it fractures into history. Dust and microcollisions lack the cinematic drama of an asteroid impact, but in their cumulative weight, they may prove just as lethal. They gnaw at Atlas day by day, testing strengths and exploiting weaknesses built over billions of years. The comet that once drifted serenely through the cold dark is now undergoing a crucible no interstellar visitor has yet faced. Whether it endures or dissolves, Atlas is revealing through struggle, through strain, what it means for an ancient wanderer to confront the hazards of our crowded celestial neighborhood. And the outcome, suspended between resilience and ruin, remains an open question, written one spark, one crack, one grain of dust at a time. In the summer of 2025, just as the world's gaze locked onto the strange visitor known as 3I Atlas, a paper surfaced that would ripple through both scientific circles and popular imagination. Posted as a speculative preprint on RxIV, it carried the name of Harvard astronomer Abraham Loeb and collaborators. They framed it as a pedagogical thought experiment, but the suggestion inside was anything but ordinary. Perhaps Atlas was not a comet at all. Perhaps it was a crafted machine, an interstellar artifact, maybe even one with intentions that were not benign. For those who remembered Loeb's earlier arguments about the first known interstellar object, Oumuamua, the idea felt familiar. He had once proposed that its peculiar acceleration and lack of cometary outgassing could be signs of alien engineering. But Atlas was a different enigma. This one was active, with the coma and tail of a textbook comet, yet its arrival and its path through the inner system seemed suspiciously well-timed for close observation. The language of the paper was cautious, hedged with qualifiers and acknowledgments of uncertainty. But in the media environment of 2025, restraint was soon lost. Headlines blared about alien spacecraft and possible hostile probes, reshaping nuanced speculation into sensational storylines. Social media fed the fire. Commentators exaggerated the claims, while critics rushed to ridicule them. A feedback loop emerged. Cautious hypotheses became bold declarations, then global talking points. Meanwhile, the scientific establishment responded with calm. NASA classified Atlas as a natural comet and pointed to spectroscopic evidence. Normal cometary volatiles were present, though in ratios not typically seen in our solar family. Observations with the James Webb Space Telescope confirmed the release of carbon dioxide and water vapor, exactly the sort of sublimation expected when sunlight warms a nucleus of ice and dust. The chemistry was unusual, but not unprecedented. Most telling of all, none of the signatures that might indicate artificial origin had been found. Radio astronomers scanned the sky, searching at frequencies used by human technologies, but detected only the faint thermal whisper of natural radiation. The comet's brightness, charted night after night, showed variations that matched the rotation of an irregular, lumpy body, far from the steady gleam one would expect from a polished sphere or engineered cylinder. Its acceleration, too, fell in line with natural outgassing rather than propulsion. The timing argument, why now, why here, proved less mysterious when dissected. Orbital dynamics is a stern master. Interstellar bodies can only arrive along certain pathways, and those that pass close to the Sun are also those most visible to our telescopes. That Atlas's trajectory brought it into regions where spacecraft could observe it was not evidence of intent, but of probability and opportunity. Its flyby distance from Mars, cited by many as too perfect, turned out to be a typical range for hyperbolic interlopers. The only extraordinary factor was that humanity now had instruments in place, ready to capitalize on the moment. Still, the speculation offered an unexpected benefit. SETI researchers seized the opportunity to mount passive campaigns, scheduling global networks of radio dishes to listen as Atlas swept past Mars and curved toward the Sunday. They searched not only for artificial transmissions, but also for the possibility of smaller probes, escort craft, or released fragments that might betray purposeful design. No such evidence emerged. What they heard was silence, and what they saw was a comet behaving like a comet. Yet silence can be compelling in its own way. It left the mystery intact, suspended between imagination and data. Atlas, in its shimmering wake of vapor and dust, carried both the weight of scientific scrutiny and the allure of myth. Was it only a relic of primordial ice, thrown into our skies by the blind mechanics of gravity? Almost certainly, but in daring to wonder otherwise, humanity once again revealed its hunger for stories that reach beyond ourselves, stories that strain against the boundary between science and dream. When astronomers turned their most powerful instruments toward 3I Atlas, the results told a story far less dramatic than the headlines, yet no less profound. High-resolution imaging campaigns revealed no companions drifting alongside it, no jets of matter vented with deliberate precision, no geometric regularities etched in its luminous coma or trailing tail, nothing that would hint at an engineered machine. Instead, the spectrographs whispered a quieter truth. The chemistry of Atlas bore the unmistakable stamp of nature. Its emissions were rich in carbon dioxide, an oddity by the standards of solar system comets, but not outside the possibilities of astrophysical theory. Models of planetary nurseries around distant suns predict exactly such compositions in bodies birthed in the cold, outer reaches of alien protoplanetary disks. Even more telling were the isotopes. Ratios of these atomic fingerprints aligned with values produced by the slow furnaces of stellar nucleosynthesis, not with the artificial signatures that advanced technologies might leave behind. What the data offered was not proof of alien design, but a deepened reminder of how varied and unfamiliar natural cosmic chemistry can be. Yet speculation itself served a purpose. It forced astronomers, philosophers, and communicators alike to confront a pressing question. How should science, and the society around it, respond when confronted with phenomena that seem to defy expectation? The case of Atlas echoed earlier debates surrounding Oumuamua. Both objects carried peculiarities that did not fit comfortably into local experience, sparking conjecture that reached well beyond the academic community. But the path from cautious hypothesis to public imagination is rarely straight. Subtle hedges in scientific papers, their careful notes that speculation was pedagogical, provisional, and designed to expand thinking were often lost in translation. By the time the story reached mainstream headlines, the alien probe hypothesis was framed not as a teaching exercise, but as a serious scientific proposal. This distortion reflected more than journalistic appetite. It drew from cultural memory. Oumuamua had already primed audiences to view interstellar visitors through a lens of mystery. Centuries of science fiction had seeded images of silent probes, enigmatic artifacts, and first-contact dramas. Against this backdrop, the unusual chemistry and trajectory of Atlas seemed ready-made for narratives of cosmic intrigue. The genuine scientific excitement surrounding its strangeness could be and often was recast as evidence for something extraordinary. Yet beneath the cultural theater lay ethical questions that remain untested. Suppose one day the evidence did not dissolve under scrutiny. What if an interstellar visitor truly bore the hallmarks of intelligent manufacture? The Atlas debate functioned, in its own way, as rehearsal. It forced discussion of disclosure, transparency, international coordination, and the responsibilities of scientists who might hold knowledge that reshapes humanity's place in the cosmos. For Atlas itself, however, such speculation found no support in the sky. Its path through the asteroid belt in late 2025 obeyed the unyielding mathematics of celestial mechanics, not purposeful navigation. Its chemistry, while exotic, spoke of ancient natural processes, materials condensed in stellar nurseries beyond our own, drifting for eons before chance delivered them here. Far from diminishing its significance, this natural origin made it all the more precious. Atlas was not a messenger from an alien intelligence, but a shard of another world's history, carrying samples of matter sculpted in foreign suns. The true mystery was never whether Atlas was a machine. It was how nature herself, in the crucibles of other stars, could fashion bodies so unlike those familiar to our solar experience. That is the question worthy of pursuit, as urgent and as awe-inspiring as any dream of science fiction. As Atlas arced toward its fiery encounter with the sun, the drama was not one of control versus autonomy, but of survival. Would this ancient traveler endure the furnace long enough to divulge the secrets of its alien chemistry? Or would it fragment into silence, scattering its story into the void? The unraveling of Atlas would not be a single moment of catastrophe, but a slow and haunting spectacle. At first, the signs would be subtle slight shifts in brightness, uneven jets of gas spraying into the void. Yet these hints would betray a deeper crisis unfolding within its ancient core. After billions of years wandering the interstellar dark, the comet would find its undoing, not in a cosmic collision, but in the steady, merciless heat of the Sunday. Solar energy, once distant and faint, now drills deeper into its nucleus. Volatiles buried for eons begin to vaporize violently, pressurizing pockets within the ice rock framework. Old fractures, carved by countless thermal cycles across interstellar ages, become fault lines for sudden outbursts. Each venting event tears at the integrity of the whole until the nucleus itself begins to split. Observers would see the transformation in striking clarity. The once compact core, a bright point of reflected sunlight, would stretch and fracture into multiple knots of light. High-resolution imaging would reveal a family of fragments, drifting apart under the combined push of rotation and escaping gases. Within days, the comet's brightness would surge, then flicker, as each fragment briefly flares before exhausting its volatile layers and fading into inert rock. The coma, once crisp and focused, would dissolve into a hazy cloud. Its tail would grow chaotic, braiding into overlapping filaments of ionized gas, while the dust stream would fan outward like a broken banner, vast and diffuse across the night sky. For those on Earth, the sight would be at once magnificent and tragic. The disintegration could produce a burst of brilliance, lifting Atlas into naked-eye visibility, a fleeting jewel against the heavens. Yet this spectacle would come at the cost of the comet's heart, the destruction of untouched interstellar matter, material that once held the secrets of other suns. What could have been a priceless archive of cosmic chemistry would be scattered irretrievably into dust. The question of danger inevitably follows. Would Earth face a meteor storm born of this celestial shattering? In Atlas's case, the answer is reassuring. Bound to a hyperbolic trajectory, its fragments would follow the same outbound path, racing past the sun and away from our orbit. Unlike the periodic comets that lace Earth's skies with debris trails, this traveler's remnants would never cross our world. The only traces left behind would be delicate, perhaps a temporary brightening of the zodiacal light as dust thickens in some regions, or a faint increase in radio hiss as the expanding ion cloud tussles with the solar wind. These phenomena, though ephemeral, would enrich scientific study while sparing Earth from harm. And so, from the perspective of planetary dynamics, the fall of Atlas would barely ripple across the solar system. But to human eyes and hearts, it would be a paradox, an interstellar visitor breaking apart in brilliance, gifting us a fleeting spectacle even as it takes with it the last chance to study its untouched core. A shattered messenger, luminous in its undoing, vanishing into the endless dark from which it came. The total mass of this celestial traveler, estimated at no more than a few trillion tons, is astronomically impressive in scale, yet cosmically insignificant. Compared with the vast gravitational currents that dictate planetary orbits, such a quantity barely registers like a grain of dust adrift in an ocean storm. Even if every fragment of 3I divided by Atlas were to collapse into a single clump, its gravitational tug would remain invisible to even our most delicate instruments. This insignificance in mass, however, is contrasted by the enormity of its scientific value, particularly if the nucleus were to fracture. Fragmentation brings with it a dilemma. On one hand, the breakup of the nucleus erases a structural integrity that has been preserved for billions of years. The carefully layered architecture, which once recorded the history of accretion, formation, and chemical distribution in another star's nursery, becomes scrambled beyond recognition. The internal record of how dust and ice coalesced layer upon layer over countless eons is effectively destroyed. Once the internal materials are stirred and dispersed, the chance of reconstructing their original arrangement vanishes forever. Yet there is another side to this coin, one that excites astronomers. Fragmentation lays bare what was once hidden beneath weathered exteriors. Fresh surfaces gleam in the dark, revealing pristine ices and volatile compounds that had slumbered beneath radiation-scorched crusts for billions of years. Where once the comet's chemistry was locked away, inaccessible to our instruments, sudden ruptures offer a raw glimpse into alien chemistry. Spectroscopy of these fracture planes could disclose subtle isotopic fingerprints and rare molecules invisible in the intact body. The expanding debris field itself becomes a gift. As fragments drift apart, the total reflective surface grows, amplifying the comet's visibility and allowing telescopes to catch faint signatures that would otherwise remain concealed. We have seen this drama before. Comet Ison, a fiery visitor, and C divided by 2019 Y4 Atlas, a namesake cousin, both displayed familiar patterns. At first they brightened spectacularly, their increased surface areas sparkling as sublimating ice released trapped gases. But this brilliance was short-lived. Small fragments, quickly bleeding their reserves of volatile material, dimmed into obscurity. Their debris clouds stretched thin along their orbits, lingering as ghostly trails before fading into invisibility. Months, sometimes years, were enough to erase their presence entirely. These case studies serve as templates, teaching us what to expect if Atlas itself were to break apart. High-resolution imaging is crucial here. The Hubble Space Telescope has, in the past, captured unforgettable portraits of disintegrating comets, fractured nuclei separating like beads on an invisible thread, each piece spinning off into its own solitary path. Such images do more than inspire, they provide hard data on whether the rupture stems from internal stresses, external collisions, or the relentless thermal pounding of solar radiation. Looking ahead, the European Space Agency's Comet Interceptor mission, set for launch in the late 2022, may offer an even closer perspective. If Atlas fractures, its debris might not be a single target but many, each a shard preserving a different aspect of the ancient whole, an unintended laboratory scattered through the void. But beyond the science lies the poignancy of fate. Imagine an object older than mountains, older than the continents beneath our feet, voyaging between stars since the galaxy's youth. It has survived the bombardment of cosmic rays, endured encounters with wandering giants, and drifted through the icy vacuum of interstellar space for unthinkable spans of time. For such a voyager to meet its end not in some catastrophic collision, but under the quiet heat of our familiar sun, that is a story that resonates deeply. Humanity has always looked at comets as symbols of impermanence, flares of beauty that blaze briefly before dissolving into nothingness. Atlas elevates this symbol to galactic scales. Its demise would remind us that even journeys spanning billions of years can dissolve in what is, on geological timescales, the blink of an eye. Yet even destruction would not rob Atlas of its legacy. Its fragments, drifting outward into the solar system, would continue their mission in silence. Carried across decades or even centuries, they might one day be intercepted by spacecraft, their isotopes and minerals still whispering secrets of their ancient origin. Observations of its breakup would refine our models of cometary structure, improving our grasp of how such bodies form, evolve, and perish. For scientists, a shattered nucleus is not merely a loss, it is a revelation, a sacrifice of form for knowledge. The evidence that Atlas could succumb has always lingered in its erratic brightness, a sign of mounting internal strain. Destruction, then, is not failure. It is transformation, a final act in which survival gives way to disclosure. As the comet races toward its perilous October approach to the Sun, the universe offers us a choice of endings. Perhaps the wanderer will endure, emerging battered yet whole on the far side of perihelion. Or perhaps the ancient lattice of ice and dust will finally unravel, releasing its secrets in a luminous farewell. Either outcome holds meaning. In survival, we glimpse resilience across eons. In destruction, we gain sudden access to chemistry sealed since the galaxy's youth. Atlas, whether whole or shattered, reminds us that we live in a galaxy dense with wanderers, emissaries from other suns whose stories are only beginning to reach us. Its fate, unfolding before our telescopes, is a lesson not only in astrophysics, but in perspective, a testament to the fragile grandeur of worlds that drift between the stars. The idea of redirecting an interstellar comet into a permanent orbit around the Sun has stirred imaginations since the very first detection of such visitors. The dream is simple but powerful. Could a single chance encounter with a planet slow Atlas down enough to transform it from a fleeting stranger into a lasting resident? For many, this fantasy satisfies an almost mythic longing for companionship in the void, an ancient traveler abandoning its endless exile between the stars to live among our familiar worlds. Yet the equations that govern celestial mechanics allow little room for wishful thinking. Atlas carries with it extraordinary energy, expressed through what astronomers call hyperbolic excess velocity. At nearly 58 kilometers per second, this velocity represents a momentum that dwarfs anything the planets can counteract. For comparison, Jupiter, the most massive planet in our system, can only shift a comet's speed by about 2 kilometers per second, even during an unusually close pass. Such a nudge, while vast by human standards, is nothing more than a minor course correction against the comet's staggering head start. In truth, the energy required to capture Atlas would demand erasing more than 99% of its motion, an impossible feat for any gravitational ally in our solar neighborhood. Gravitational capture requires what orbital theorists call a deep encounter, a close, intimate approach where a massive world can bend a trajectory through sharp angles, sapping energy through tidal effects or other dissipative means. For Atlas, the closest planetary flyby will occur at Mars, but at a separation of 0.19 astronomical units, tens of millions of kilometers away. This is, by capture standards, a distant handshake rather than an embrace. Even Venus, which the comet will pass at 0.65 AU in November, can only add subtle deviations. None of these encounters will erase its hyperbolic nature. They may adjust its course, changing the fine details of its solar passage and the angle of its eventual departure, but never binding it to the Sunday. Yet subtlety itself is fascinating. Tiny shifts in timing, entry angle, or orbital tilt could be enough for astronomers to measure and study. Non-gravitational forces further enrich this picture. Comets do not simply follow Newton's laws in silence, they breathe. Jets of gas erupt from beneath their crusts as they near the sun, acting like natural thrusters. These outbursts may seem trivial, but over time, they accumulate into measurable accelerations. The Rosetta mission showed this vividly with Comet 67P Churyumov-Gerasimenko, whose asymmetric jets altered its orbital period by minutes every revolution. For Atlas, with its unusual carbon dioxide-rich chemistry, these jets might behave differently than those of water-dominated cousins, producing distinct and perhaps more forceful deviations. Even so, the comet's hyperbolic trajectory is too deeply etched for such whispering engines to reverse. They may change the exit doorway, but they cannot stop the departure. Speculation has even imagined Atlas hiding within the asteroid belt, slipping unnoticed into the throng of local bodies. But orbital mechanics tolerates no disguise. A hyperbolic path cannot loop into a closed orbit, no matter where it threads through the solar system. Like an arrow shot from beyond the horizon, its fate is to pass through, never to linger. Still, the scientific potential of this passage is immense. After disappearing behind the Sun during conjunction, Atlas will re-emerge in early December 2025. Observations then will be critical. Any changes in trajectory, however small, will reveal the combined influences of planetary perturbations and cometary outgassing. Such data will refine our models of interstellar bodies, helping prepare us for the inevitable future visitors. Moreover, the opportunity is not confined to Earth-based telescopes. Multiple spacecraft scattered across the inner solar system may capture glimpses, offering parallax views that sharpen our understanding of its orbit. The Mars encounter on October 3, in particular, presents a rare chance. Orbiters like NASA's Mars Reconnaissance Orbiter and MAVEN, the European Mars Express, and even rovers on the surface could all, under the right circumstances, spot this luminous traveler. The coordination required to schedule such observations would be complex, but the rewards direct images and data of an interstellar comet brushing past another world would be profound. In the end, Atlas will not stay. It will not be captured or tamed, and it cannot be hidden in the asteroid belt. But in its refusal to linger, it still grants us something valuable, a living experiment in cosmic dynamics, a chance to witness how even small forces, planetary nudges, and cometary breaths sculpt the journey of an object born beneath another Sunday. Its story is not one of belonging, but of passing through, reminding us that the universe is filled with wanderers whose paths cross ours only once before vanishing back into the dark. Though the trajectory shifts of 3I Atlas are vanishingly small, their significance reaches far beyond a matter of orbital mechanics. Every subtle deflection offers clues to how interstellar objects interact with planetary systems like our own. By tracing these changes, astronomers can refine models of how such wanderers evolve over eons, and better anticipate how often future surveys might detect them. More critically, The delicate deviations serve as natural experiments, testing our grasp of the hidden forces at play: non-gravitational nudges from outgassing jets, the steady push of solar radiation, and the invisible embrace of the solar wind. If Atlas leaves on a path that diverges measurably from the course predicted by gravity alone, we will know that these forces have etched their influence into its journey. Each data point becomes a fragment of knowledge, revealing how alien material responds when immersed in a stellar environment. Its ultimate destiny, however, is not in question. Atlas will exit the solar system on a hyperbolic arc, its speed too great for capture. The exact angle of departure and the moment of crossing into interstellar darkness may shift, but the outcome is immutable. It will return to the galactic wilderness. For us, that brings both loss and comfort. Loss, because this emissary cannot be tethered for long study. Comfort, because it carries with it traces of our own system dust, radiation signatures, perhaps atoms swept up along the way back into the interstellar medium. In that sense, Atlas becomes a cosmic courier, sampling the chemistry of different suns and scattering it across stellar neighborhoods over spans measured not in millennia, but in galactic ages. No dream of redirection can rewrite the physics of such a voyage. This traveler is, and always will be, a visitor. When it departs, we are left with its data, its fleeting glow, and the haunting reminder that the galaxy is threaded with ancient wanderers. Atlas will vanish into the dark, carrying its mystery intact, while we hold on to the questions it leaves behind, questions that may endure longer than our own civilization. What began as a quiet academic exercise in the summer of 2025 soon evolved into one of the most divisive debates surrounding 3I Atlas. A single preprint uploaded to Arxiv planted the seed. Could this wandering body represent not a natural comet, but alien technology? At first, the authors, Abraham Loeb and colleagues, had treated the question as a teaching tool. Their paper framed the hypothesis in careful, tentative language. Phrases like possibly hostile were not predictions, but examples to illustrate how far the scientific method demands we stretch our imagination before ruling anything out. The intention was to remind readers that extraordinary claims require extraordinary evidence, and that even outlandish scenarios must be judged by their ability to generate testable predictions. But once released into the public sphere, speculation grew unchecked. Media outlets, driven by clicks, highlighted the most sensational phrases while ignoring the caveats and mathematical caution. Social platforms magnified this effect, rewarding bold headlines over nuance. Within weeks, what had begun as a narrow academic thought experiment had metastasized into breathless claims of alien probes and galactic surveillance. The progression was a study in how scientific speculation can be warped by public imagination into narratives that outpace the evidence itself. The scientific community, meanwhile, remained grounded. NASA classified Atlas as a natural comet, citing multiple independent lines of observational data. Spectroscopy from the James Webb Space Telescope and ground-based instruments revealed outgassing consistent with sublimation, even if its chemistry was unusual compared with familiar solar system bodies. Crucially, none of the hallmarks of artificiality appeared. Radio surveys detected no coherent transmissions at communication frequencies. Optical monitoring revealed no controlled acceleration beyond the subtle nudges of volatile jets. High-resolution imaging showed no geometric structures suggestive of engineering. The principle held: the burden of proof rests with those making extraordinary claims, and in this case, the evidence simply was not there. Still, SETI researchers embraced the opportunity for observation. Breakthrough Listen and other survey programs scheduled dedicated campaigns during Atlas's approach, perihelion passage, and departure. They listened carefully for any signals that might betray technological intent. Yet silence prevailed. Negative results in science are not empty, they carve away at possibility space, ruling out hypotheses that predict clear signatures. If a probe were transmitting at common frequencies, we should have heard it. If controlled maneuvers existed, we should have seen them. Instead, the comet behaved in ways that fit natural processes. Even the search for companions, miniature probes, detached objects, structured ejector turned up nothing. Hubble, adaptive optics arrays, and wide-field telescopes scrutinized the coma and tail, finding no patterns inconsistent with natural fragmentation. More telling still were isotopic ratios of carbon, oxygen, and hydrogen. These fingerprints bore the mark of stellar nucleosynthesis, not artifice. They aligned with expectations for material forged in galactic nurseries, not factories. And yet, the alien hypothesis refused to vanish, not because evidence sustained it, but because culture did. The shadow of Oumuamua lingered, that enigmatic visitor which first inspired whispers of technology hidden in plain sight. Science fiction had already furnished a ready-made narrative. Probes seeded across the galaxy, silent watchers drifting through planetary systems. Each new interstellar object was bound to inherit this mythology. Media seized upon it, weaving headlines that suggested more than the data supported, often downplaying the scientific restraint at the heart of the conversation. By the time Atlas crossed the asteroid belt, the tension between sober science and public imagination was stark. For researchers, the evidence pointed overwhelmingly to a natural body. For segments of the public, the allure of alien technology proved too tempting to resist. The debate thus became not just about a comet, but about how humanity digests the unknown, how speculation, wonder, and narrative intersect with data, discipline, and proof. The headlines were irresistible. Scientists say comet could be alien probe, but what was lost in translation between research papers and public reporting was the caution, the probability ranges, and the alternative explanations that scientists had carefully laid out. This was not so much a failure of science as a test of science communication in the age of instant headlines and viral algorithms. How should researchers walk the line between bold speculation and public clarity? What responsibility do they bear when their words are sensationalized, stripped of nuance, and amplified into something closer to fiction than fact? The uproar provided an unexpected teaching moment. For educators and communicators, the alien probe hypothesis became a living classroom, an example of how science proceeds from idea to test to conclusion, and how extraordinary claims require extraordinary evidence. Students of astronomy could see, in real time, how the process of peer review, replication, and scrutiny helps separate speculation from established knowledge. It wasn't just about comets. It was about the integrity of scientific method itself. Yet there was also an ethical shadow. Suppose real evidence of artificial construction ever appeared. Who should disclose it? How should nations respond? How would communication be managed in a world where information can leap from preprint to headline in hours? The Atlas controversy became a rehearsal of sorts, a glimpse of the dilemmas humanity might face when confronted with a truly anomalous discovery. And perhaps the greatest irony was this: the alien hypothesis, while wrong, highlighted how astonishing Atlas was in its natural state. Its chemistry rich in carbon dioxide, unlike anything in our local stellar nursery, spoke of birth conditions utterly foreign to our sun's neighborhood. Its trajectory, threading almost along the ecliptic, reminded us that interstellar space is populated with bodies on every imaginable orbital path. Even the timing of its detection spoke volumes, a testament to our growing ability to spot visitors that would have slipped unnoticed through earlier generations of telescopes. In truth, Atlas, as a natural body, was far more compelling than it would have been as a machine. Technology, however advanced, is bound by the logic of engineering and purpose. Nature, by contrast, plays by rules we do not fully grasp, under conditions we can scarcely imagine, and produces results that astonish us precisely because they escape our expectations. The true mystery was not whether aliens had built Atlas, but how distant stellar environments had forged something so alien to our own experience. As the comet pressed onward through the asteroid belt, evidence stacked overwhelmingly in favor of a natural origin, not because the idea of extraterrestrials was absurd, but because the universe itself is strange enough. It does not need alien architects to produce wonders that strain our imagination. The alien probe idea had served its purpose. It provoked observation, sharpened analysis, and captured the public's attention. But in the end, the natural explanation proved the most extraordinary of all. Atlas reminded us that reality, when viewed on a galactic stage, can be stranger, more beautiful, and more surprising than any invention of science fiction. The detection of Atlas was more than just another entry in an astronomical catalogue. It was a wake-up call, a glimpse into the future of skywatching. For centuries, comets and asteroids bound to our sun have dominated our charts, their orbits predictable for generations ahead. NASA, ESA, and ground-based surveys have logged millions of these permanent residents. But interstellar visitors are a different breed entirely. They arrive suddenly, slipping in from random directions, follow hyperbolic arcs that cut straight through our neighborhood, and vanish into the dark within weeks or months. Their appearances, like Oumuamua, Borisov, and now Atlas, are less a product of routine surveillance than of fortuitous timing and sheer luck. This element of chance will soon shift with the arrival of the Vera C. Rubin Observatory, once known as the Large Synoptic Survey Telescope. Beginning in the mid-2022, Rubin will scan the southern skies every few nights, building a decade-long record with depth and precision unmatched in astronomical history. Its relentless gaze could multiply our detection rate of interstellar wanderers, perhaps 1 or 2 per year in conservative scenarios, or dozens annually in more optimistic models. Such a flood would transform interstellar objects from rare curiosities into a steady stream of emissaries, each carrying the chemistry and memory of alien suns. The scientific payoff would be staggering. Studying just one object reveals isolated secrets, an isotope ratio here, a peculiar chemical pattern there. But with many visitors, patterns emerge. Echoes of planetary birthplaces, fingerprints of stellar nurseries, hints of galactic evolution written into their icy cores. This shift from anecdote to statistics could redefine our understanding of how worlds form and how galaxies seed them. Yet abundance brings new challenges. Coordinated campaigns, like those mounted for Atlas, are difficult to replicate if discoveries arrive monthly. The astronomical community will need rapid response protocols, automated detection systems, and telescopes ready to pivot at a moment's notice. Atlas itself served as rehearsal. The collaboration between NASA, ESA, NewLab, and partners worldwide showed how swiftly resources can be mobilized. The rapid redirection of Hubble and the James Webb Space Telescope proved the value of flexible scheduling and priority overrides, and the public spectacle that followed from measured scientific announcements to global fascination underscored the importance of communication. Interstellar objects ignite imagination as much as science, and guiding that fascination responsibly has become part of the astronomer's craft. Beyond science and media lies a subtler concern: planetary defense. If these wanderers are not just icy messengers but potentially hazardous projectiles, then detecting, tracking, and characterizing them swiftly becomes essential. Atlas reminded us that our solar system is not a closed world, but part of a galactic thoroughfare. Its discovery was not just a story of science, but a signal. The universe is sending visitors more often than we once dared to believe, and we must be ready to greet them. Though Atlas itself posed no danger to Earth, it underscored a sobering truth. Future visitors may not be so harmless. Some may cut trajectories that thread closer to our planet, or graze its orbital path, telling apart the benign messengers from those with potential for catastrophe requires speed and precision, fast orbit determination, accurate size estimates, and advanced tracking systems. While our surveys are improving, they remain works in progress. The technology, however, is catching up. Machine learning algorithms are now adept at picking out faint, moving points of light in vast seas of data, rivaling the sharpness of human eyes. Automated follow-up systems stand ready to trigger spectroscopic observations across facilities worldwide, guided by predetermined criteria. Within hours of discovery, information can cascade through international communication networks, ensuring no time is lost. As these visitors grow more common, their scientific and educational value multiplies. Each discovery becomes a teaching tool, a living case study in stellar birth, planetary dynamics, and galactic chemistry. Their diversity is perhaps the greatest gift. Some echo familiar solar system objects, while others bear no resemblance to anything we know. Together, they create natural laboratories for a discipline we might call interstellar planetology, comparisons across worlds born under different suns. Yet abundance brings challenges. Every well-documented encounter generates mountains of data, terabytes of images, spectra, and light curves that must be processed, archived, and preserved for decades of future analysis. Atlas itself has left behind such a dataset, a benchmark that will serve as both archive and touchstone for interpreting the flood of discoveries to come. No single nation or observatory can shoulder this alone. As detection rates climb, international cooperation becomes more than desirable, it becomes essential. Telescope time must be shared, observation schedules coordinated, expertise pooled across borders. Atlas demonstrated the effectiveness of such global synergy, but future encounters will demand even more structured frameworks, agreements that transcend institutional and national boundaries. The ripple effects stretch beyond telescopes. If interstellar objects prove common, they justify ambitions long relegated to theory, dedicated interceptor missions. Imagine spacecraft positioned strategically around the solar system, primed for rapid deployment, ready to chase down a newly spotted interstellar wanderer within weeks. The blueprints already exist in the literature. What they await is justification in the form of sufficient detection rates. Amateurs, too, have their role in this unfolding story. With CCD cameras and computerized mounts, astronomy has been democratized. Armies of dedicated skywatchers, coordinated through digital networks, can provide continuous monitoring impossible for professional observatories bound by tight schedules. The age of interstellar visitors is not only a scientific revolution, but a cultural one, drawing citizens into the very frontier of discovery. Yet perhaps the most profound lesson of Atlas is philosophical. Each visitor is not just an object of ice and dust, but a messenger, carrying the chemistry of stars we may never reach. They remind us that we are not isolated but woven into a galactic ecosystem where matter and possibly life wanders from system to system. The iron in our blood, the carbon in our cells, the oxygen we breathe were forged in distant stars and flung across space by supernovae. In studying Atlas, we are not examining strangers but long-lost kin, members of the vast family of cosmic materials. As Atlas sweeps toward its solar encounter, it has already reshaped our expectations. It has revealed a sky more dynamic, a galaxy more interconnected than earlier generations dared to dream. The visitors yet to come will carry this education forward, turning fleeting curiosities into routine encounters, transforming wonder into a new normal. The wake-up call has sounded. The age of interstellar wanderers has begun. As Atlas races through the final corridors of the asteroid belt, preparing for its October confrontation with the Sun, it brings with it more than ice and dust. It carries meaning, a mirror held up to humanity, reflecting our place in a cosmos far richer and stranger than our ancestors ever conceived. Whether this wanderer survives intact, unravels slowly under the sun's heat, or scatters spectacularly across our skies, its message has already been delivered. It is a messenger of the galaxy, and every spectral reading, every shift in brightness, every fine structural detail captured through our telescopes is another line in the story of how matter migrates across stellar systems, transporting the chemistry of distant worlds into our sight. Its retrograde path, threading through the densest corridors of our solar system, reminds us that the universe is not orderly and confined, but dynamic, filled with traffic flowing in every direction. Gravitational tides that shape planetary orbits also guide the aimless wanderings of bodies born around other suns, creating encounters that bridge the immense gulfs of interstellar space. In this way, Atlas is not merely a comet, it is a bridge, a fleeting connection across light years. Its chemistry, rich in carbon dioxide and revealed by the James Webb Space Telescope, whispers of alien birthplaces. Ratios of volatiles, subtle isotopic fingerprints, and physical traits testify to protoplanetary disks governed by unfamiliar balances of temperature, radiation, and elemental abundance. What is ordinary in one corner of the galaxy becomes extraordinary when carried across billions of years and trillions of kilometers. Atlas is no miracle, no supernatural aberration. It is the natural product of planetary formation under conditions just different enough from our own to challenge what we thought we knew. These subtle differences, magnified by cosmic time, have sculpted an emissary that defies our local expectations. The implications stretch beyond science into philosophy. The gases now sublimating into sunlight were frozen into solid form when the Milky Way was young, when clusters of stars were being born and dying in nurseries we can scarcely glimpse today. Each reflected photon and every spectral line is a thread binding us to an epoch billions of years before Earth even formed. We are, in effect, watching history itself escape into space, not the history of our planet, but of galactic environments long gone, carried in microcosm by this lone traveler. Human ingenuity has risen to meet the challenge of decoding this relic. The coordination of Webb, Hubble, and countless ground-based telescopes with theoretical modeling has turned us into cosmic archaeologists, piecing together histories written long before humanity existed. Yet Atlas also reminds us of our vast ignorance. It is but one data point in a population of billions, one shard from the Milky Way's thick disk. The full spectrum of chemistry and structure among its kin remains almost entirely hidden, waiting for us to develop the tools to uncover it. The practical implications of its discovery foreshadow what lies ahead. When the Vera C. Rubin Observatory begins its decade-long survey, interstellar visitors may no longer be once-in-a-generation marvels, but routine discoveries. The techniques refined in the study of Atlas rapid characterization, coordinated observation, careful public communication will serve as rehearsals for that era. We are preparing for a future where the galaxy's wanderers arrive often enough to become familiar. For Atlas itself, the question of danger has been settled. its trajectory poses no threat to Earth. What it does pose, however, is an invitation to see ourselves within the broader circulation of matter through the galaxy, to recognize that our sun and planets are not isolated, but part of a vast and ever-moving interchange of cosmic material. Atlas is both messenger and mirror, urging us to confront the immensity of time, the diversity of creation, and our own fragile but profound place in a universe filled with countless other journeys. At a distance of 1.8 astronomical units, Atlas passes Earth from a position of safety. Even in the event of complete fragmentation, its debris would scatter along the same hyperbolic path, flung outward into interstellar space rather than drawn inward toward our planet. This reassurance allows scientists and the public alike to observe without fear, to savor the rare opportunity of a cosmic visitor free from the anxiety that shadows near-Earth asteroids. In this case, curiosity is unchained from threat, giving us the space to ask what this ancient wanderer reveals about galactic evolution, planetary formation, and the chemistry of stars beyond our own. But Atlas is more than an astronomical subject. It is also a cultural event. Its presence stretches human imagination, reminding us that our solar system is not a closed sanctuary, but part of a wider cosmic highway. The knowledge that objects from distant stars drift into our skies changes our sense of place. We are not alone in the sense of alien civilizations watching us, but rather in a subtler way, through matter itself. The dust Atlas releases into sunlight will mingle with the zodiacal cloud that already veils our skies, interstellar grains becoming part of the same haze that includes fragments from the birth of Earth. Future spacecraft, perhaps even human explorers, will pass through this material unaware of its remarkable origin. What was once alien will become indistinguishable from the fabric of our local environment. In this way, Atlas embodies both a guest and a contributor. The comet itself will not linger. It will sweep around the sun, then arc back into the galactic wilderness, never to return. Yet it will leave something behind, a trail of gas, dust, and ice that fuses with our solar system, subtle but permanent additions to our cosmic household. In that sense, Atlas becomes not only a messenger, but a participant, joining interstellar history with our own. The science it brings is equally enduring. Even before perihelion, the most important lesson has already been delivered. Atlas is proof that interstellar space holds a diverse population of wandering bodies, each carrying chemistry shaped by stars far removed from our Sunday. Its spectral signatures show that alien environments can produce materials that stretch our theoretical frameworks, forcing us to revise what we thought we knew about cometary composition and galactic chemistry. Its journey demonstrates that the solar system is no isolated island, but part of a dynamic web of exchange, a great circulation of matter that spans the Milky Way. When Atlas fades from our telescopes, whether intact or scattered, it leaves us changed. It has revealed that our place in the galaxy is one of participation, not isolation. Our atoms, our water, our dust, these are not unique creations, but part of a network of materials cycling across eons and systems. Atlas speaks in the timeless language of physics and chemistry, a voice echoing from before Earth was formed. Its message is clear: we have always been connected. The mirror it holds up to us reflects not solitude but kinship, not exception but continuity. And as Atlas departs, the story does not end. Somewhere in the void, another traveler is already on its way, carrying new messages from stars we will never see directly. The conversation of worlds continues, written not in words but in trajectories of ice and stone, in the eternal dialogue of wandering bodies that bridge the gulfs between suns. Picture this: a relic of unimaginable age, older than every mountain and ocean on Earth, now speeding through our solar system. To imagine its voyage, think of an antique machine racing down a cosmic highway strewn with hazards no eye can see. That is the path of 3I Atlas as it threads its way into the asteroid belt. But unlike a car, this traveler is more than 4 billion years old, and the road ahead stretches across millions of kilometers. Any impact along the way could shatter it forever, obliterating one of the rarest glimpses we've ever had into alien chemistry. Each moment, this interstellar wanderer etches a new line in its survival tale, plunging deeper into the dense shooting gallery of rock and ice that drifts between Mars and Jupiter. The marvel lies not only in its journey, but in our chance to witness it unfold in real time, a fleeting drama written against the backdrop of eternity. Can this ancient giant endure the most perilous crossing of our celestial neighborhood? And what story will the fragments tell if it fails? For now, let the odyssey of 3I Atlas carry you forward into mystery, danger, and the awe of the unknown.